All right, let's look at some practice problems for 6.1, reaction rates. So our first type of example has to do with us finding a rate when we're given a change in concentration over a change in time. So these questions are a little bit more straightforward. All you have to do is pay attention to what's given in the question. So the question is asking you, what is the overall rate of production of ammonia? So this is ammonia in this system. So this particular reaction. Notice that it's already balanced, so we don't have to do that. If the concentration of ammonia is 3.5 moles per liter after 60 seconds and 6.2 moles per liter after 240 seconds. So given this information, I need to find the rate of production of ammonia. And remember that rate is the change in concentration over the change in time. And that works here because I'm given two values of concentration and two values of time. So I can find the change in concentration and I can find the change in time. So let's start with the change in concentration. So the change in concentration, it starts off as 3.5 moles per liter. And then after 240 seconds, it's 6.2 moles per liter. So all I have to do is subtract 6.2 moles per liter minus 3.5 moles per liter in order to figure out the change in concentration. Now the change in concentration is then divided by the change in time. And the change in time, I do a similar thing, 240 seconds minus 60 seconds. 240 seconds minus 60. All right, now if I find these values, the change in concentration is 2.7 moles per liter, and the change in time is 180 seconds. If I divide these two values together, I get 0.015 moles per liter times second. So that's how you do that first example, or any example where you're asked to find the rate by using the change in concentration over change in time formula. Now in the second example, you were asked to find the rate by looking at stoichiometric ratios. So in this example, you're given a reaction. So this is a reaction. Again, it is balanced. If it's not balanced, make sure that you balance it or else this ratio would not work. If the rate of disappearance of N2O5, so that's N2O5, is 5.6 times 10 to the negative 2 moles per liter times second, then determine, and I'm asked to find first, the rate of appearance of O2. So I can use my stoichiometric ratios and the rate that I'm actually given. So I'm given the rate of disappearance of N2O5, and I can use that to find the rate of O2. So let's start out by writing out, so rate of O2, that's what I'm trying to find, is equal to, and I always have to start off with the value that I'm actually given. And in this case, that is 5.6 times 10 to the negative 2 moles per liter times second. Now, when I'm referring to moles here, 5.6 times 10 to the negative 2 moles, I'm talking about moles of N2O5. And if I'm looking at the rate of O2, I need to convert this value of moles to moles of O2. How do I do that? I can use dimensional analysis. So let's look at the ratio between, this is supposed to be 2, between N2O5 and O2. So the ratio between N2O5 is 2 to 1. So what I'm going to write down at the bottom here is 2 moles of N2O5. And up at the top, I'm going to have 1 mole of O2. Now, if I'm setting this up this way, what this allows me to do is cancel out the moles of N2O5. So when this multiplies out, the value that I'm going to have, the unit, is going to be moles per liter times second. So it's still going to be moles per liter times second, but the mole value is going to be of O2. And when I multiply this out, my answer is 2.8 times 10 to the power of negative 2. All right, let's do another problem. In this case, I'm looking for the appearance of NO2. So rate of NO2 is equal to, I do the exact same thing. I start off with the value that I know, that I'm given in the question, 5.6 times 10 to the negative 2 moles divided by liter times second, times, I'm doing the same thing here. When I'm saying moles, I mean N2O5. I need to figure that or change that into moles of NO2. So I look at the ratio between N2O5 and NO2. It's a 2:4 ratio. So at the bottom, I'm going to write 2 moles N2O5, 4 moles NO2. My moles of N2O5 cancel out. So my unit again is going to be moles per liter times second. That makes sense. It's a rate value. And if I multiply these values out, I'm going to get 1.1 times 10 to the power of negative 1. And that's it.